So in this video we have arrived to section D in the chapter, which is called Differentiation with multiple inputs and outputs, the Jacobian matrix. Okay? For context, remember the slide that I'm using often. So far in this chapter we have studied this case here, when we have several variables and a function which is a scalar. So we have seen the partial differentiation of f with respect to the variables. But now finally we are going to go to the most general case. So this is a function which is a vector that depends on several variables. Okay? And we are going to see how to do partial differentiation in this most general case. So this is the situation right here. We have our function f, which is a vector. Notice that this is in bold because it's a vector, okay? And f is a vector that depends on several variables, x1, x2, up to xm, which are the input variables, okay? So if you think in terms of this machine with the knobs, you have m knobs in the input, and when you change each of these knobs, all of the output knobs change, okay? So this is what a variable that has multiple inputs and multiple outputs look like. And the way to define the partial derivatives for this function is actually to define something that we call the Jacobian matrix. And this is a very simple concept. The Jacobian matrix is a matrix which usually is called J, whose elements are all the different combinations of partial derivatives of each of the outputs with respect to each of the inputs. Okay? So for example, the first row will be the partial derivative of f1 with respect to x1. Then it will be the partial derivative of f1 with respect to x2. And so on until the partial derivative of f1 with respect to xm. Okay? And here f1 is simply the first component of the output vector. Next, the second row is the partial derivative of f2 with respect to x1. The next element is the partial derivative of f2 with respect to x2, up until the partial derivative of f2 with respect to xm. And so on, we do it for each of the elements of f until we do the partial derivative of fn, which is the last component of the output vector, with respect to x1. Then the partial derivative of fn with respect to x2, all the way up to the partial derivative of fn with respect to xm. Okay? So in this way, we fill in a grid which has n rows and m columns. And this is a matrix which contains all of the first order partial derivatives. Okay? And the nice thing about defining this matrix is that now the total differential is very easy to calculate. So the total differential, df, and now f is a vector, is equal to a column vector containing the total differential of each of the output components of vector f. Okay, remember vector f has n output components. So this is vector f. So each of the elements of this vector, which is the differential of vector f, is the differential of the different components of f. And you know, when you studied the total differential, that the total differential of f1 is simply partial of f1 with respect to x1 times dx1 plus partial of f1 with respect to x2 times dx2 plus ... until partial of f1 with respect to xm times dxm. So that is for df1. So we substituted this into this, which is a single number, okay, or function. Next, we do the same with the total differential of f2, the second component of f. And this will give us this second function. And then the final element of this vector is the total differential of the last component of vector f, dfn, which is given by this function here. So if you look at this can actually be written, this is a vector, okay? This is a vector of n rows, So this is a vector with n rows and only one column, yeah? But it can be written very elegantly as the Jacobian matrix that we just defined multiplied times this vector, this column vector, which we call dx, the differential of the inputs, dx, yeah? And it contains dx1 as the first element, dx2 as the second element, up to dxm as the last element, okay? In other words, if we remove all these intermediate steps, what we find is that df, the differential of our vector f, is equal to the Jacobian matrix times dx, the differential of the input variables. Okay? And this would summarize this most general case. So this is interesting because this is very similar to what you knew in one dimension. So let me do in a corner here, let me write, remember one dimension. So in one dimension, f of x, you know that df is equal to the derivative of f with respect to x times dx, right? By using the chain rule. So this equation right here is equivalent to this equation. So df is the differential of the output, which in this case is a scalar, but here it's the differential of this vector f, and it's a vector. Dx here is the differential of the input, which is a scalar, and here dx vector is the differential of all of the inputs put into a column vector. And then J, the Jacobian matrix, plays the role of the derivative of f with respect to x. So J, the Jacobian matrix, is the generalization of the derivative to the most general case of many inputs and many outputs.